Well, thank you very much, Mr. Chairman, and thank you for the invitation to give a talk to this very interesting symposium. So I will talk about ultrafast MRAM strategies for cache applications and beyond. And my talk is organized as follows. I will start just giving a very brief introduction about spintronics and SPINTEC, what we are, positioning of MRAM in the memory hierarchy, and after I will discuss some strategies we are developing in SPINTEC for high-speed switching, and I will summarize. So first of all, about SPINTEC. So SPINTEC is a research lab which was created in 2002, having now about 100 people working on the field of spintronics and being located in Grenoble area in between big research institutes for fundamental research, but also nearby Leti. So our positioning is to cover this spintronics from the very fundamental science up to applications. So, in order to do that, of course, we have expertises going from material processing, test, CMOS magnetic integration, but also we have an in-house design team doing design, analog, digital, and going up to system performance evaluation. So, spintronics, I will not go into detail. There were two very nice introductions yesterday from Tohoku University, just to say that in order to do nice devices with the spintronics, we have to master some basic building blocks, which are what we call magnetic heterostructures, to deal with the spin-dependent diffusion, to deal with the magnetoresistance, so dependence of the resistance with respect to the applied field of the injected current, or new effects allowing recently to manipulate the magnetization using spin polarized current, either the spin transfer or spin orbit torque. So of course, spintronics has some applications which are of interest today in the low power electronics field for MRAM and non-volatile logic, but there are a lot of other things, and racetrack, memory store applications, RF devices, which can be either STT or SOT, in magnetic nanoparticles, energy sensors, and magnetic recording. So magnetic memories, of course, historically speaking, there were some actually big steps starting from the discovery of the tunnel magnetoresistance at room temperature, new concepts proposed by Everspin up to their product in 2006, which was the toggle MRAM. It took about 10 years to move from the experimental evidence of this tunnel magnetoresistance up to the product. Now, in terms of spin transfer torque, from the theoretical prediction of Johnson-Slanczewski in '96, it took longer to implement it, even now there are some in-plane and perpendicular prototypes which are samples to customers. So, of course, from the beginning, and I'm taking some pictures which are from Grenoble area, showing that typically MRAM memories were from the beginning considered as having some nice advantages and having combined advantages with respect to other memories, being non-volatile, like flash, dense, potentially like DRAM, fast, like SRAM, and having high endurance. But of course, up to the implementation into the market, there were different flavors which evolved from what we call field-driven to the STT MRAM, having different flavors, either in-plane magnetized or perpendicular, using some what we call precessional switching assisted with thermally heat, or more recently what we call the three-terminal devices, allowing to write the magnetic memory by a current which is not passed anymore through the tunnel barrier, so with advantages in terms of cyclability. Of course, as I mentioned, you have to have this main block of the MTG, which is actually a tunnel barrier giving a magnetoresistance which is dependent on a relative orientation of two magnetic layers. In reality, is much more complicated, and you have many layers. And so you start from a very simple actually burger, and you put different flavors in it, of course trying to make it better, faster, and so on. So this was a bit why it was so complicated maybe to arrive quicker to a product. So of course it took long time, but there were some recent progress on the industrial side recently, some announcements from 2017 showing either Samsung, TSMC, or Global Foundries in partnership with Everspin of new developments in the MRAM field. So this is very nice and promising. So on SPINTEC side, of course, from the creation of the lab, we covered the different concepts I was talking about, from the thermal assist up to the three-terminal device. There were some startup companies started from SPINTEC, including Crocus Technology, which is now more focused on magnetic sensors. Evader is doing microcontrollers using either MRAM and resistive RAM, HProbe more on electrical test, and Antios on the three-terminal device. And also we had some funding from the European Union, of course, going to the STT, classical STT, but also using the spintronics for RF and integrated functionalities, sensors, RF, and memory. And more recently, we also have a project funded on all optical switching that Professor Boko will talk about more in the next talk. So let me just go now into the positioning of the MRAM in the memory hierarchy. So of course, if we are looking to the ITRS roadmap, we can see that if we look at the power consumption with respect to the future, we can see that there will be a big increase in the switching power, namely for the logic part, even if of course we can see that there is also an increase in blue for the memory part. So what we call the logic part is the part which is above the working memory, so above the cache. And for that, in order to reduce the power consumption, we can see that typical memories which are located here are namely volatile memories. So bringing non-volatility at this level could be of interest. So of course, in order to bring non-volatility, we have to deal with this issue of the speed mismatching between the memory and the CPU, and the actually difference in the working frequency of the two means that the logic keeps awaiting data, and finally the logic issue is becoming a memory issue. So now, how fast is fast enough? Because in order to go into this logic part, okay, we have to deal with different frequencies, and if we look to the speed, we can see that typically for the DRAM replacement, we are in the 3 to 20 nanoseconds, so actual perpendicular STT RAM can do the job, but if you want to move to cache replacement or closer to the processor, you will need a sub-nanosecond switching MRAM. So this is the concept I will talk about today. So I will propose 3 different concepts, named 1, 2, and 3, and will be described in the next part of the talk. The one is what we call the precessional switching. A second one is a regular STT perpendicular, but using, you will see a small tilt in the anisotropy. A third one, which was already described yesterday, is what we call the SOT, which is potentially very fast, but is a larger footprint. And Professor Boko will talk about this all optical switching. Okay, so let me introduce this precessional STT-MRAM with perpendicular polarizer. So we know that in order to do the switching of the magnetization in either in-plane or perpendicularly magnetized structures, you have to inject the current with a current density which is large enough in order to induce the switching of the magnetization of the storage layer. Now, if you look at the dependence of the evolution of the magnetization with respect to polarization and magnetization, we can see that there is a dependence which is a vectorial product in between the polarization and magnetization. So actually, in order to have a torque, you wait for the thermal activation to induce a small angle in order to start the reversal. This is why, if you look at the switching probability, you can see that in between 1 and 10 nanoseconds, there is a probability of having switches at different times. So this was actually shown for either in-plane or perpendicular magnetized junction. So we have a kind of stochastic reversal having what we call an incubation time, which precedes large thermal fluctuation. So this is why, in order to have reliable STT-MRAM writing, but also with relatively low power consumption, this will require more than few nanoseconds for the writing. So one solution is to bring into the system what we call the non-collinearity or perpendicular polarizer, which is added on top of the structure. And the advantage of adding this perpendicular polarizer is that now the dependence of the STT is given by two terms, one coming from the in-plane analyzer, which is giving our bipolar switching with the stochastic behavior, but also a second term coming from the perpendicular polarizer, which is giving out-of-plane oscillations and giving this initial triggering of the magnetization. Now, the whole thing is how to tune the relative influence of the two terms from the STT contributions. And I'm describing two potential strategies, one using the shape and second one using a small transverse magnetic field. So macrospin simulations indicated that for an aspect ratio of 2, and these are actually the cell size we measured in the lab to demonstrate this proof of concept, are showing that for this perpendicular polarizer, if we look at dependence of the current density with respect to the pulse width, we can see stripes of reversal in between one and the opposite direction. And actually, if we are doing actually a cross section through this, we can see a dependence of the magnetoresistance with the time. Is the basic principle of what we call a RF oscillator. The advantage being that we can tune the frequency of the rotation of the magnetization of the storage layer with the current density. So now, if we move to larger aspect ratios, and here is aspect ratio of 5, we can see that this switching diagram is largely modified, and we do not have anymore these alternating stripes. We can obtain a non-oscillatory bipolar switching, and we can achieve from the simulation ultra-fast reversal without an incubation time. And we demonstrated this on magnetic tunnel junctions, which are prepared in the lab. Of course, in order to have this conventional structure, we have to add on top of the magnetic tunnel junction a perpendicular polarizer, which is either separated by a copper spacer or a magnesium oxide. And in order to look at the reversal of the magnetization, we are using real-time measurement experiment. So what these measurements are saying is, if we are looking to the dependence of the electrical signal either in single shot or mean traces values, and this is for an aspect ratio of 2, we can retrieve this oscillatory behavior of the magnetization. Of course, the number of cycles is actually increased with the increase of the voltage which is applied to the junction, giving this linear dependence in between the frequency and the current density. We also obtain that typically a dephasing in the precessional motion, which can obtain with pulse duration which is in the 500 picosecond range, is that a dephasing of the precessional motion for the same junction is obtained in less than 10 nanoseconds. Now, if we modify the aspect ratio, now we move to an aspect ratio of 5 with the same type of measurements, we can see now that depending again on the voltage which is applied across the junction, we can obtain switching which varies from few nanoseconds to less than 1 nanosecond. And if we plot the switching probability as a function of the pulse width, we can see that the large aspect ratio allows for non-oscillatory, fast, and direct overwrite switching. And in terms of energy, if we go to the quickest switching for 0.8 volt, we have an energy per writing event of 90 femtojoule. Now, of course, this is nice from the reversal point of view, but the question is, of course, using such a large aspect ratio are not very good for the integration. So, of course, we also demonstrated that adding a small magnetic field, we can go to circular junctions and obtain bipolar switching. Okay, so let me talk about a second strategy for switching we used. So typically we start now from perpendicular STT-RAM, classical, and we play with what we call the second order anisotropy. Anisotropy being the property of the magnetization to be actually preserved in a given direction. So if we look to the magnetic switching of perpendicular STT-MRAM, we can see that typically the dependence of resistance versus applied field, if we apply the applied field along the perpendicular direction, so what we call an easy anisotropy axis, is very well defined with no steps. Also, we have a switching diagram in between the pulse voltage and applied field, indicating either for the voltage and the applied field a well-defined working diagram. However, these rectangular loops without intermediate state or micromagnetic distortions are not giving directly an information about the switching mechanism, either if it's a nucleation propagation or a coherent rotation. So in order to have a more detailed information about the anisotropy itself, we perform for different diameters of the perpendicular STT-MRAM going down to 50 nanometer at different temperatures. These are versus H dependence measurements. So, okay, we can have information about the variation of the resistance with respect to temperature and so on. But what is important from physical point of view is if we model this hard axis behavior by we can do it only by introducing what we call a second order anisotropy in the formula. And this second order anisotropy actually is confirmed by VSM magnetic measurements or resonance frequency measurements. So why is interesting now to look at this dependence with the second order anisotropy from the electrical properties point of view. So these are actually simulations indicating switching diagrams which are obtained for right pulse duration which are for example 50 nanoseconds, in which we modify the ratio between the second order and the first order anisotropy. So here there is no second order anisotropy, and here we increase it gradually. So what we can see is that the shape of the switching diagram is preserved, but the transitions either in voltage and in the field are modified, and typically by adding this second order anisotropy reduce both the switching voltage and both the writing field. And in the STT there is a figure of merit, which is actually the ratio between the switching current and the stability, and we can obtain that adding this second order anisotropy is helpful in order to increase this figure of merit. Now, secondly, if we go to smaller pulse duration, which is at 1 nanosecond, we can see that this gain is even more important. So we are going from a figure of merit of 1.5 to a figure of merit of 2.4. This actually confirms that this second order anisotropy provides an initial angle which will trigger the magnetization reversal and will be helpful for the reduction of the switching current. Of course, all this has a compromise in the retention value, so we have to find second order anisotropy which reduce enough the switching current but not degrade too much the retention. So finally, on the high-speed SOT-MRAM, I will not enter into detail because there were some presentations from Tohoku yesterday on this concept. So just saying that this SOT-MRAM, even if is relatively... Yeah, spin orbit torque MRAM. So instead of having spin transfer torque, we have a spin orbit torque. So typically you have an asymmetric system in which a cobalt is sandwiched in between a aluminum oxide and a platinum layer, and actually we can switch the magnetization only by a current which is passed through the platinum. So we obtain a switching probability which actually can be achieved at 100% depending on the current which is injected in switching pulses which are down to 180 picoseconds. Of course, if you are looking to the dependence of the switching diagram, we can see that typically for the switching, we still have to apply a very small magnetic field. So there are actually strategies under study in order to remove completely this perpendicular magnetic field. What is also actually interesting, and what we did in the framework of a European project called SPOT, is that we try to replace memory parts, so namely SRAM, from the L1 to L3 by MRAM, and we did a cross comparison in between the different combination. So the first name here depicts actually the L1 memory, what type of memory it is, and the second one is the L2. So what is interesting to mention is that adding SOT or STT has some advantages in terms of area reduction and also in terms of energy consumption. So the best compromise we found from our evaluations were that adding SOT-MRAM at L2 or L3 allow a reduction of the energy consumption by 60% and a reduction on the area by 30%. Okay, so to summarize my talk, so I discussed about some ultra-fast MRAM concepts in order to go above the cache level. So I'm proposing 3 strategies: a perpendicular polarizer or precessional switching, use a second order anisotropy in the conventional STT-MRAM, and also using this 3-terminal device which is SOT. Of course, all optical switching is also of interest, and you will see that the switching speeds are even smaller. What is also interesting for the spintronics, just to finish with this, is that the magnetic tunnel junctions are allowing not only memory and logic operations, but also analog operations. So what we are doing right now in the field of Internet of Things is to combine together functionalities from a given stack, given magnetic stack, but giving at the same time 3 different functionalities in a single chip, either memory, sensor, and RF. So I would like to thank all the contributors to this work, coming from SPINTEC, but also from our collaborators from University Paris Sud, Samsung, Singulus, Leti, and ATH in Zurich. And I would like to thank you also for your attention.
Is open for discussion. Many eager questioners.
So on one of your early slides, you showed a millivolt difference between the on and the off state. So at the end, you said full SRAM. So I think for full SRAM, we need to have VDD difference between the on and the off state, or do you need a readout on each?
Yeah, maybe it was just the initial slide in order to indicate the magnetoresistance. So right now in industry we have values of TMR which are 200% about. So typically these are giving much larger delta variation in between R. So it depends on what's the diameter, but typically, yeah, you can have much larger variation.
Thank you for the talk. The speed looks, I think, reasonable. It's doable. My worry, however, is the density. I don't think you're trying to beat SRAM. I understand the non-volatility is extra, which is great, but you're trying to beat EDRAM. EDRAM is going to be 3x. And if you look at 10... embedded DRAM.
Yeah, I prepared a slide.
Right. So the sizes I've seen for 10 nanometer and 7 nanometer, just the MTJ size looks too big.
So of course, for very small dimensions and for this embedded DRAM, of course, there are still some I would say challenges in order to reduce the size, which are related to the process itself and to the complexity, to the thickness of the stack itself. That's the main driver for Samsung, for example, for embedded DRAM. So typically they are working on that. So it's not an easy task, but people are working.
So I really liked your section on the second order anisotropy, especially since we're often told not to ignore the second order, and it's nice to see it actually being used. So a couple of questions about that. One is, oh no, okay, well, okay. One is, okay, how do you expect to tune this in the material?
Yeah, so typically this second order anisotropy can come from either variability of the, I would say, boron migration, from the thickness variation, or grain size. So typically, just playing with the thickness or the composition of the cobalt and boron, what content of boron inside, we already have experimental results showing that we can tune this K2 value.
Okay, I have a quick one.
Yeah.
The companies are going to offer this as some kind of a foundry service, and so what are the companies actually going to offer?
What
is Samsung is offering? What are they offering exactly?
So for the moment, nothing. But in principle, for labs or for the advanced research, the idea is to offer an MPW in order to test all your ideas. I think Global Foundry will offer it quicker than Samsung.
Okay. So let me go ahead and introduce Jeff Boker.